In the movie remake, Total Recall in 2012, there appears an interesting transportation system which didn't show up in the original movie. The transportation vehicle is called Fall and travels through a long tunnel which goes through the earth. What if we make the tunnel and get inside? 1. We will fall and stop at the center of the earth. 2. We fall straight forever and move away from the earth. 3. We move back and forth in the tunnel. Hello everyone, how's it going? I'm Professor Peter. If you make the tunnel like in the movie and drop an object in it, what will happen? Obviously, we can't make this tunnel and vehicle, but we can figure out how the object moves in the tunnel using physics. In the movie, the fall takes 17 minutes to arrive at the opposite side of the Earth.
17 minutes.
And the passengers experience the upside down of gravity during the travel. Are these true? Let's figure that out. First off, we need a couple of assumptions. First, the fall doesn't have any engines or propulsion system. Second, the tunnel goes straight through the center of the Earth. Third, we will ignore the effect of tunnel in the mathematical analysis because it's very narrow. How much gravity force is applied to the apple in the tunnel like this? As the apple gets closer to the center of the Earth, will the gravity force increase or decrease? Let's briefly review the law of gravitation. According to the Newton's law of universal gravitation, the two objects here attract each other. The magnitude of the attraction force is proportional to the two masses and inversely proportional to the distance squared. If you multiply the gravitational constant on this, you can calculate the gravitational force. To calculate the gravity force on the apple that is in the tunnel, we need shell theorem. If there's a spherical shell and we put an apple in it, the gravitational force acting on the apple becomes zero, no matter where you put the apple. This is the first outcome of the shell theorem. To prove this mathematically, you should carry out the challenging integration. Here, I'm going to briefly explain without equations. Since the apple is surrounded by the shell, various sizes of gravitational forces are applied to the apple in various directions. If you add the forces together, the resultant force becomes zero because the forces cancel each other. What if the apple is outside the shell? The second outcome of the shell theorem is that the gravitational force on the apple outside the shell is the same as the force from the concentrated object of the shell at the center. In other words, to consider the shell with the mass m, you can just replace the shell with a point mass m. You need a complicated integral calculation to prove it. For those who are interested in the mathematical proof of the shell theorem, I'll put some information about it in the video description. Now, if the apple is placed there, how much gravity will be acted on it? According to the shell theorem, we can divide the Earth into two areas based on the position of the apple, inside and outside. The outside region doesn't affect the apple. If you split it into multiple thin shells, you notice that each shell doesn't make any contribution to the gravity on the apple. As a result, we don't have to consider the outside region in calculating the gravity on the apple. As we assumed, we ignored the effect of the tunnel because its width is so small compared to the size of the Earth. Now, let's consider the remaining inside region of the Earth. To apply the shell theorem, we split it into many thin shells like this. To know the effect of each shell, you can just replace it with a small object with the same mass. Consequently, we can just consider a small object placed at the center with the same mass of the inside region. Interestingly, the gravity force is changing as the apple moves. If the apple is away from the Earth's center by the distance x, the inside region of the Earth has the volume 4 pi over 3 times x cubed. If we multiply the Earth's density d, we can get the mass of the region. To compute the gravity force, we multiply this calculated mass of the Earth, the mass of the apple m, and the gravitational constant g, and divide it by the distance x squared. In the simplified result, we have a variable x and all other constants. That is, the gravity force on the apple is linearly proportional to the distance between the Earth's center and the apple. The direction of the force is also important. It is always pointing to the center of the Earth. So it is to the left in this case and to the right in this case. This is very similar to an object hanging on a spring. When the object goes to the right, the spring pulls it back to the left. And when the object moves to the left, the spring pushes back to the right. The amount of spring force is proportional to the travel distance x of the object. This relationship between the spring force and the travel distance of the object is called Hooke's law. Here the parameter k is the spring stiffness. The spring force is the stiffness times x. Consequently, the apple in the earth tunnel will go back and forth like an object hanging on a spring. If the fall starts free fall in the tunnel, it'll move at the maximum speed when it passes the center of the earth, and it'll temporarily stop at the opposite side of the earth. The speed change is well demonstrated in the movie, and it doesn't need any engine or propulsion. Of course, this is all true in theory. Now, let's see if this travel takes 17 minutes for a one-way trip as shown in the movie. According to the second Newton's law, F equals ma, the spring dynamics can be written as ma equals negative kx, where m is the mass of the object, a is the acceleration, k is the spring stiffness, and x is the displacement of the object. We have the negative sign on the right-hand side of this equation because the spring force is always in the opposite direction of the movement of the object. Actually, this is a differential equation. If you solve this equation, you can get the natural frequency of the repeated motion of the object. Its reciprocal, 2 pi square root of m over k, is called a period, which is the time to take to travel from the right end to the left and then come back to the starting position. The time of one-way trip is the half of the period, which is pi square root of m over k. Previously, we found the equation for the force acting on the apple like this. Using this equation and the spring dynamics, we can compute the equivalent stiffness in the Earth tunnel system. Then, we plug this information to the time formula for the one-way trip. In addition, we put the gravitational constant g and the Earth density d in the equation. And we conclude that the time for a one-way trip is about 42 minutes. Even though it is longer than 17 minutes in the movie, it is not that bad for the long-distance travel. Next, let's talk about the gravity upside down described in the movie. We can feel the gravity because we overcome it and stay on the ground. Since we are not moving, but our hair and arms are pulled down by gravity, we feel the gravity downward. This becomes more clear if you see astronauts. Their hairs are floating and arms are lifted high unnaturally because they're in the zero gravity situation. There is another way that we can feel zero gravity, that is to fall with an airplane. This is totally different from the acceleration in the car. When the car accelerates, you can feel the pushing force from the car seat. However, when you free fall with an airplane, you are not pushed down by the airplane. Both you and the airplane are pulled down by the earth. That's why you feel as if you are in the zero gravity situation. If you apply this reasoning to the movie, the seats of the fall will not push or support the passengers during the free fall. In principle, they feel zero gravity during the entire time of the travel. I think that the movie shows this in a little different way. One more thing, it is impossible to build this transportation system. You need too much energy to build this tunnel structure, and it'll be very hard to maintain it. It seems very dangerous to pass through the hot core of the earth, doesn't it? That's all for today. Thanks for watching. See you next time. Bye bye.